Good afternoon, everybody. I'm Savary. I'm PhD student at Marseille University, and I came to present you a lecture entitled Low Noise Smart Sensor based on silicon nanowires MEMS resistive microphone. We'll introduce a smart sensor, then we'll introduce MEMS project and the main actors. M&M's theory of operation will be explained, and smart sensor topology will be shown. Then, we'll go deeper into the readout circuits, and some implementation schematic and simulation results will be shown before conclusion. Smart sensor is a sensor that contains all you need to get physical to digital information. They are widely spread over customer electronics detection and measurement systems. They are used anytime a digital unit needs to have a look of what's happening in physical world. Faced to the growing interest and the technological challenge, the MEMS project was created. It is supported by the French National Research Agency and 4 entities. The CE, the 3 laboratories working on acoustic modeling, sensor design, readout circuits, and a company working on biomedical implants. Thus, it involves power consumption issue, packaging, and integration. M&M sensor relies on nanowires piezoresistivity and the fact that we can combine 2 different dimensions, nano and the micro. This is the so-called micro and nano mechanical. This is the so-called micro and mechanical. In one end, you have the nanowires, and in the other end, you have micromechanical structures that strange the nanowires. Then, a resistance change can be observed by the readout circuits. Due to the different scale, we have the opportunity to create lever effect, so the applied strength can be very important. Here is a photograph of an M&M's accelerometer that was realized in a previous work. We see the nanowires here, and we see the seismic mass, the moving seismic mass. The smart sensor will contain the transducer providing analog information. It could be voltage or currents with respect to the acoustic vibration, an amplifier, and a data converter. One important matter is that human ear feature has very large dynamic range. It's 100 dB over the frequency range of 20 to 20 kilo. So data converter will have to handle the dynamic range over the frequency band. And state of the art pointed out sigma delta modulator as the best way to achieve high resolution to fit human ear feature. Thus, our readout circuit will be based on sigma delta, where resolution is governed by 3 main parameters: the quantizer resolution, the order of the loop, and the oversampling ratio. Choosing 1 bit resolution quantizer will allow us to be free from mismatch error, especially when using deep submicron technology, where mismatch can be very important. 1 bit quantizer are always linear. Then, the oversampling ratio and the 4th order of the loop will push quantization noise completely out of the audio band. When implementing the sigma delta, there are two possibilities for integration. We can use discrete time integrators or continuous time. Continuous time integrator has the advantage that anti-aliasing filter is not required because the sampling process takes place at the end of the loop. So we can save the pre-filtering stage. The problem of this kind of architecture is the clock jitter sensitivity. One important properties of this topology is that some coefficients are zero. Thus, some path can be removed. Considering that we do not need anti-aliasing filter and there is no feed-forward path from input to output, we can directly connect the sensor at the modulator input. We choose Western bridge arrangement because with a constant current, it has the advantage that temperature effects are removed and current can directly feed the integrators. Since floating nodes current source does not exist, we have to use two current source and to equate the source current and the sink current to avoid common mode current. This is the implementation schematic. It's very simple because we use for the very first chip RC integrators. There are 4 integrators, the summing amplifier, the clocked comparator, and the current mode feedback. The sensor is connected directly at the input of the first integrating stage. We implemented the circuits on a 65 nanometers technology that is suitable for further for implementing digital filter. Here are some simulation results of the modulator and the amplifier. The spectrum analysis of the pulse density modulation show that we can achieve the resolution, but we have to improve integrators to remove these spurious tones that corrupt spurious-free dynamic range. Here is a audio frequency band. Amplifier noise is shown on this graph. We designed the first amplifier to reach the lowest possible noise density. This simulation does not include the amplifier noise, so we expect a higher noise floor when the chip will be tested. Here is the layout of the chip and the die photo. There is nothing very interesting on the die photo because it's very small and optical cannot see what's inside. But the layout is interesting. This is the area occupied by the sigma delta modulator, and here is the biasing circuit. And other units were designed and implemented for test and measurement purpose here is an amplifier. To conclude, a complete readout circuit for a MEMS-based audio sensor was designed and implemented in a deep submicron technology that is suitable for heavy digital signal processing. Measurements are in progress. We have received the chip a few weeks ago, and we are on study for a new design with a reduced power consumption to address biomedical application. And finally, it's planned to do system in package, or if we can, system on chip with both readout and sensor on the same die. Thank you for your attention.